All right, I think we'll get started. Nice to meet everyone. My name is Goku, and I'm joined here by a couple folks from Anyscale. We got Balaji, who works on the Ray Data team, and Akshay, who's an engineering manager for about half of the work that we do at Ray at Anyscale. Um, we're going to be talking about multimodal AI workloads today and kind of the challenges and how Ray can really help address some of these challenges. And just mention it one more time, but all the material that you're going to see today, slides, code, everything is going to be available for you guys. We'll send out an email afterwards with all the relevant links. And we also have, I think we have a Q&A session, which I can't see, but I think you guys should be able to ask Q&A there, and then we'll have folks on the team answer those. And we have this split across a few small sections today. So after each one, we'll go through the Q&A for each subsection as well. Okay, so nice to meet everyone. Work on machine learning and product here, and today the agenda is going to be mostly interactive. So I'm going to quickly talk about the challenges of multimodal AI, if you guys are not already familiar. And then we're just going to jump into the code and take a look at some of these challenges in action and how Ray helps address all of these. Awesome. Um, You guys probably are going to see a poll right now. Maybe just take a few seconds to answer this. We're just curious kind of what your experience with Ray is so far. And based on that, we can kind of add more info while we're talking. And then we also want to know if you are using Ray, how are you putting them into production already? Okay, awesome. I see answers coming in. And let's get started. So, there are a lot of challenges with AI already, but when you're trying to do things both at scale and then with multimodal AI, mixture of all these different modalities today, audio, video, text, there's a lot of challenges. And the first one that I think comes to a lot of people's minds is compute. Even getting compute can be a challenge, but when you do have it and you have a workload that you're trying to run, you're going to want a heterogeneous compute cluster, right? It's not just CPUs, not just GPUs. It's a mix, and it's not just one type of GPU. You can have a variety of GPUs if you're actually doing things right. You want to put your largest models maybe sharded across the right GPUs, and maybe not waste large GPUs on smaller workloads and models. And so you get the GPU, you create this heterogeneous cluster, and now you want to make sure you're actually utilizing them well. We oftentimes, before a lot of teams end up using Ray, utilization rates can be as low as, 10, 20%. So you're paying a lot of money, but you're not really using the compute that you actually have. And then certainly getting your dependencies for the actual workloads is another challenge and getting them on not just your main head node that you might be working on, but across all the different worker nodes in your cluster is also a challenge there. Okay, um, so you've got the compute, and there's certainly a fair share of challenges there. Now it's about scale. You have your workload defined maybe in your, with Python, with the tools and libraries that you already love, and it works maybe on your laptop. But then now, how do you actually scale this and still stay in the Python ecosystem? You shouldn't have to learn a completely new language or paradigm to scale things. And how can you scale it in such a minimal fashion that it doesn't require you having to rewrite all of your code? And while you're doing this, you also want to make sure that you have the same observability, if not better, and debugging experience like you do on your local laptop. And when you're working across thousands of nodes, that is extremely difficult. And usually a lot of solutions that help you scale won't come with those things. And then while you're running these workloads, what happens if you're running a very expensive workload and then 80 or 90% of the way through something fails? And there's always going to be things that fail, right? Whether it's just a worker node that fails and that's out of your control, or something in your code breaks, you hit an exception, whatever it is, the ability to have fault tolerance and automatic checkpointing to resume the job once the issue is resolved and continue from where you left off is going to be really important, especially for these more expensive and longer running workloads. And then certainly we have uh, the actual challenge, and this is true for whatever modality or scale you're working with. How do you go from the work that you just did during development to production? If your development is a very small cluster or your local laptop, you're going to automatically have a ton of drift when you go to production. Everything's different. The compute cluster is different. The environments may be different. The code that you had before may not work. And that's going to require another kind of huge effort there to port that over. You also want to be able to quickly iterate once you have something in production, and you want to do that in a way that doesn't make what you currently have in production go down, and your users are kind of sitting there without a service or whatever it is that you're offering. And you certainly want to make sure you hit certain SLAs like latency and throughput, and you want to be able to tweak these things based on what you're trying to achieve. So these are just some of the kind of the major challenges. We're going to keep revisiting this today as we kind of walk through the demo, but we will show kind of, no matter what model, modality, data source, wherever that's coming from, no matter what kind of compute you're using, whether it's on-prem, on the cloud, whatever types of hardware, compute at whatever scale you're doing, whatever workload you're doing, from processing to batch inference to training to online serving, and whatever framework you might be using. We've really designed Ray to kind of fit all these different patterns and workflows. And then we've added a lot more features on top of that with Ray as well, in terms of observability, debugging, the governance you may need around this. And Anyscale kind of is our managed solution to add even more kind of features to make this even better and faster. And it's easy to say things are, better and faster with Ray or Ray on Anyscale, but we're going to go ahead and show you guys what that actually looks like. So again, we're going to send all this out after the webinar today, all the code, and we also have an interactive workspace where you can run through all of this on a decently sized cluster for free. So we'll send all this out for you guys over email, but I'm going to get started with the actual demo now. So I hope you guys can see this. Let me know if you do need me to zoom in. My team will let me know. Okay, let's just set up the scene quickly. So it's always good to, when you're showing something like this, it's a good idea to actually walk through the overview of what we're trying to build. And I love actually demonstrating things with an actual application and not just kind of talking about them at some high level. So what we're going to be doing today is a couple different workloads. I originally had these combined, but I decided to separate them to make it a bit clearer. We're going to start with some raw data. We're going to pre-process it. We're going to do some batch inference where we take a large model and apply it to the data to generate embeddings. So this is like your canonical batch inference workload. We're using it to generate some embeddings. The data set I have today is this open source data set from, I believe Stanford, of a bunch of different dog breeds and pictures for each breed. And we're just generating embeddings from those. That's the first workload. The next two are going to be tied. So we're going to use the same raw data set to train a classifier. Um, it's not too big, but it will demonstrate kind of what distributed training looks like and how to actually make your, let's say, PyTorch, existing PyTorch code easily perform distributed training. So we're going to use that to build a classifier that can actually take these images, and then now, you could put in an image of your own dog and you can get the breeds. And then at the end, we'll go ahead and show how to actually serve this and actually in a distributed manner so that you can actually use this as an endpoint to make it available to others. Before I do get into the workload, I'm going to show you, I'm actually on a workspace right now. I was running this before the demo. This workspace here is part of Anyscale. It's just a fantastic development environment where you can, work on VS Code or Jupyter Notebook like I have here, Cursor, whatever you want. Everything's on here. And it feels like I'm on a kind of just a local setting here, but in reality, I have access to a cluster here. I've got a head node where I'm going to do most of my code. But when and only when I actually kick off a workload, we can make the appropriate worker node spin up and actually run that workload at scale and then come back down. So I had this toggled on, which basically I can just run my code and I don't have to worry about what compute do I need, what kind of instance do I need to actually support what I'm trying to do. All of that happens for me under the hood. And the really nice part about this is I'm not the fastest coder, so I'm not, while I'm actually developing, I'm not wasting time sitting on a large GPU or having, tens of GPUs just waiting for me to run a workload. Only when I actually launch a Ray job, which you'll see, the workers get spawned and execute on the workload. We're gonna see a couple other things like how dependencies are managed here, and also how we do observability and debugging, so we can actually see what's happening with our workload. And I'm going to also talk about the production piece. I may not show it, depending on the time, but we'll show kind of after you do the development of each piece, what it looks like to actually go to production. And something I definitely won't cover today is if you are kind of on the platform side of things, or you work closely with the ML platform teams, we have a lot of capabilities around governance and admin capabilities around all these different features with Ray and Anyscale. So be sure to check out kind of all the links for that kind of stuff. Okay, let's get started with the first workload. So again, simple workload where we just take some data. We're gonna do distributed data ingest. We're going to pre-process it. It's going to be pretty minimal. And then we're going to generate embeddings using a model, a pre-trained model. And then we'll go ahead and store them back up to a shared storage location. So I'm just going to go ahead and pip install a couple packages here. I'm not going to focus too much on the machine learning code because I'm sure a lot of you are familiar with it, but I will kind of call out the most important things. So first thing is I'm going to actually read the data. And what I have here is all the data is in this open S3 bucket. Ray Data has tons of kind of utilities for reading and writing data from various locations. You can also use other locations that you may not see on the list, but we've got all the kind of common data sources, both for read and writes covered. And the way this works is you run the work, you have your code here to ingest data from here, and actually take one to just show an example. And you can see the images are, I believe the data format are Parquet files, but you can see sorry, they're JPEGs. But with Ray, I use the read images utility, so I get the array as a return. And what's actually happening here is that both the read and the write operation that you'll see later, they're running in a distributed fashion here, which means that you can actually process the data in parallel across all these different clusters. And we actually don't need to load the data entirely into memory either. And this is a pretty efficient thing because imagine you have a very large data set. If you do load the whole thing into memory, it's just kind of sitting there. And you also need to provision something that can support the whole thing. So Ray Data will automatically kind of break this up into various blocks, and we can just process whatever blocks need to be processed and go through that pipeline there. I have some best practices labeled out throughout all these different notebooks, but I'm going to not focus too much on these. But when you guys are going through them, you can read through these things. Most of it is just around like when to use certain things within Ray. So I do some minimal pre-processing next. It doesn't come with the classes, so I go ahead and add it. This you can see is very minimal. It's probably just something that needs to run on a CPU. So once this is no different than like base Python code that you may write. Now to actually apply this function on our all of our blocks in our data set, all we have to do is use this map functionality here, and we'll look at map matches right after this. But you can just take the raw Python function that you defined. You can now apply it to every single row in your data set. And you can specify some of these variables like how many CPUs to use and what's concurrency this should scale out at. But you can also go ahead and leave these empty, and based on kind of the compute you have, Ray will kind of adjust to what is available. Now, one thing I do want to call out here is the streaming execution. So if you weren't using Ray, so if you're using something like Spark without pipelining or SageMaker batch transform, what's happening or what would happen is that the entire data set would be read into memory. So there's a lot of waste there. And only then would you start doing your transformation. So if you're doing maps or filters and stuff like that. So there would normally be a lot of memory pressure and you'd actually have a ton of delay before your workload actually kicks off. But with Ray Data, as I mentioned, you actually start processing the chunks as soon as they're loaded and become available. No need to wait for the entire data set to load. And this is great to just avoid OOMs in general out of memory. And you start processing as soon as that first block becomes available. This is great to just overall increase the utilization of whatever hardware that you're running these on. And this is just great for kind of any kind of online style inference and with reduced latency. We've got throughout the notebooks, you'll see bunch of links as well to kind of different blog posts and benchmarks that we published over the years. A lot of these you'll notice are they're very generalizable, but some of them may be focused specifically for LLMs or different workloads. Okay, so now we had a CPU-based workload and we just mapped it, so applying it to every row in the data set. Let's take a look at what it looks like to try to scale out a GPU-based workload. So I have an embedding model here. This code is pretty generic. I just load a pre-trained model. And then I have a kind of the forward pass where I apply that model to generate the embeddings. This is there's no array here. This is just raw Python code. Now to actually apply this, I can take the data set that we had and I'm going to do map batches. So now we can apply this model's forward pass to batches of data. And again, we can specify kind of how we want to scale this, on what kind of compute, how many GPUs, concurrency, all that stuff, and that's it. You can just wrap it like this and you'd be able to apply it. Again, another best practice here around like using references instead of using the model itself, especially if you're using many, if you have a lot of concurrency, but I'm going to gloss over that for now. Okay. Um, so let's take a look at what's actually happening under the hood here. So when you chain a bunch of workloads like this, so you had, uh, we had the raw data ingestion, we had the CPU-based workload, we had the GPU-based operator there. What's actually happening is a bunch of different things. So in terms of efficiency, you were not actually going to wait for the entire data set to load, but similarly, we're not going to wait for the entire data set to go through that first CPU-based operation. As soon as a block becomes available and it's processed, it can basically go down the list of down to the next operator here. So you can see that when you kind of stagger your workloads like this, it's just great to minimize overall CPU, GPU idle time. And it works across all these different heterogeneous workloads that use heterogeneous hardware as well. Um, and the ability to scale this, you saw that we could control, the concurrency and how many GPUs per worker and all that stuff. This works at very large scale. And we've got a couple links around kind of other customers and ourselves testing that. And while this workload is running, there's a lot of reliability to get out of the box. So checkpointing. So if something were to fail, you can kind of restart from where you had left off. We also have support on the Anyscale side for the same workloads to be able to run on spot instances with on-demand fallback. And you saw that while we're developing all of this, we're not really rewriting the code. We instead were just wrapping the existing Python code with this, it was one line and specify how you want to scale it if you want to. And you're able to just run the workload at scale. So I can continue using, we're using Torch, we'll see Hugging Face later. I continue using all these different libraries that I did without scaling and just be able to wrap it to do the same thing at scale. Now we also have a lot of our customers have said, uh, these features are important, but there's a lot more they want to see on top of this. So Ray Turbo's our runtime that of Ray, same exact API as open source Ray, but it's our runtime on any scale that offers more features on top of this. So we have things like metadata fetching, just kickstart workloads earlier. We have automated auto scaling where you have kind of actors spinning up faster. You can start jobs before the entire cluster is ready if you're waiting for a lot of different resources to become available. And in terms of fault tolerance, with open source Ray, if a worker node were to fail, that would you'd be able to recover from there. But if the actual driver were to fail, that's a different story. But we've solved that in term when you're running the same workload on any scale. So the last thing I'm going to do in this workload is just actually store it. Um, again, with any scale, it comes with a lot of default storage, but you can go ahead and write this anywhere. So I have this as a shared storage here, and I'm just writing my embeddings over to there. And the workload actually kicks off at this point if you hadn't done any take or anything earlier. So you can chain a bunch of workloads and then run them at the end once you're ready to kind of write to, let's say, a file here. Okay, a couple things before we do the first Q&A pit stop here. While the actual workload is running, you have so much kind of observability and debugging tools to look at. So without kind of clicking around too much, workload I just ran, you have logs in terms of what's running, and these logs will have information on collected from all the workers, not just kind of one, so you don't have to kind of piece together where everything's coming from. You also have observability dashboard with a ton of metrics around what's happening. And again, I added links here because there's so many different views you can have here. Both on the Ray dashboard and on Grafana, you can view things like running tasks, utilization across different instance types, how things are auto scaling up and down, etc. Now, there's a ton of value here already with open source Ray here, but it can be a little overwhelming. So again, on the Anyscale side, We've added kind of workload specific dashboards to make just organizing all this information, finding bottlenecks within your workload, knowing how to actually scale this up a lot easier and faster. So you can see while I was running this data workload, you can actually see all the different operators in the workload, the progress of each one, if there's any queues being built up, what resources are being used, etc. And then obviously the unified log viewer I showed you as well. Last thing I'll mention in this workload before we go to train and serve is that how do you actually take this to production? What if I want to have I want to run this workload over and over again? I've developed it once, but I want to run this at maybe a larger scale. I want to run this with more fault tolerance, maybe retries. Maybe I want to set up queues and schedules of when to run this. That's why we have jobs. There's also an equivalent rate jobs, but I'm using the AnyScale jobs here. You can just wrap all the code that you did, that you developed. You define the dependencies. So we have a container file, very similar to a Docker file, where you can just say, these are my requirements, Debian packages, Python packages, whatever it is. You have a compute config. You can make that, again, auto select worker nodes like we have here, or you can specify exactly the compute that you want. And that's it. So you got your code, your compute, and your dependencies. Now you can just run this as a job. And I'll show you at the end how this applies to like larger CI/CD or orchestration workflows. But you can now submit the job and comes with its own view on status of the job. Once it's done, you can see logs, all of this stuff as well. I think the last thing I do here is actually just to show that the embeddings actually work. I took a picture of my own dog right here, and I just fed it in, and I asked it to retrieve like the top. I think I asked for the top five most similar images. Um, she is a border collie, but there's some smaller dogs that shows up. I'm guessing it's because of the color. So let's see if we can maybe make this a bit better with the next training and serving workloads that we do. Okay, I'm going to stop for a quick second. Akshay, I think you've been answering questions. Do you want to maybe just quickly come off, mention maybe any notable questions or if anything that you think the larger group should know?
I just see one question in the chat. It might be important to point out some Ray data capabilities here, but there's a question saying, are these images the same size or do you need to resize them? Maybe you can also just talk about general pre-processing steps and so on.
Yeah, great question. These images are all the same size. Um, uh, Sorry, actually, wait, sorry, I'm mixing up workloads. These images are actually not the same size. Um, so you can actually go ahead for generating the embeddings, it was not an issue. But I think for the training one, you'll see that I did have to resize because I was using a pre-trained model. It expects images to be a certain dimensionality. But again, our pre-processing here was minimal. You could add, um, actually, I think I showed in the next notebook in the training. You can have all your transforms be in like one function. You can apply that, and then you can have, that usually be like a CPU-based workload and then you can separate out your GPU-based stuff after that. But yeah, you can apply, just specify whatever transformations logic you want in your user-defined function, and then apply that either via map or map batches. Yeah.
Okay, we had another great question come in. How do we optimize our workloads using Ray data functionality such as concurrency? Is there a guide on or best practices?
Yeah. Do you or Balaji want to take that one? I think there's a lot that you could play around with there.
Yeah, it's kind of hard to give a general answer to how you should configure your concurrency because I think it really depends on the specific of your workload. Yeah, actually, is there anything you'd add on to that?
Yeah. So we do have a lot of observability tooling as well to help you to help guide you through setting some of these concurrency, batch size, and so on. Well, so we have this data dashboard where you can see like each stage of the pipeline that Goku was showing and where like you might have queues building up, so you can go in and um, adjust parameters to get more throughput in your pipeline.
Yeah. Yeah, it's definitely non-trivial. And that's one of the main motivations for creating these kinds of views. But this run was over. I ran it a little while ago. But you can see, as expected, the embeddings operator was the one that started to have some queued blocks. So having seen this, and you could see this not after running the whole thing, even just after running first couple blocks, you'll probably notice. So this is probably where I would adjust the concurrency, and then I should be able to see less of a queue or the queue completely kind of eradicated there. So yeah, this is definitely not a solved problem, and like Balaji actually said, it's very contextual, but we're trying to create the right tools for you to make those decisions a lot faster about how you should scale these things out. Cool. Anything else, Akshay, or should we move on to the train?
Let's keep it moving. We'll answer the rest of the questions on the train.
Okay, awesome. Okay, training now. So just to reiterate, we're going to use the same images, but this time I'm going to train a classifier just to show what it would look like to train. We're going to use PyTorch here, train a model on top of data. So we're actually going to write the actual workload as if it's just a normal PyTorch model that I'm going to be training on my local laptop. And we'll see what the delta looks like. We've got a lot of documentation around this as well for other like PyTorch Lightning and TensorFlow and maybe other frameworks you may be using. But at a high level, we're basically going to take our data. It's going to be you're going to take batches of our data. They're going to go to model replicas and then kind of all be synced up together to train one model and update the weights. And then you will show. I think I use MLflow here to save model checkpoints. So we'll see what all of that looks like, all the way from preprocessing to actually saving the artifacts and using them. Um, I don't cover RayTune to actually do the hyperparameter optimization, but that's a very popular utility as well, and I linked the page there. Okay, let's skip a couple like kind of setup here. I have the same kind of add class here because again, the dataset doesn't have that class information. I do have a dataset already split into training and validation. Just make sure that when you're doing this, that the distribution across your classes are roughly the same across your different data splits. And I defined a class that may look a little unnecessary, but I did it to just illustrate again how you'd use a class to um, apply your operations. So I convert my label that I just added, sorry, class into a label because the model needs numeric labels here. And I just have a preprocessing class that I defined that basically will do the conversion, it'll do the embedding, and then it'll just drop some unnecessary things. So why I'm actually doing the embedding here, I'll just quickly talk about the model architecture. You have your input data. Uh, if you're not doing using a pre-trained model, you'll probably have some embedding type of layer there, and then you'll maybe feed it forward, continue to feed it to a couple fully connected layers, and then you'll maybe have like a softmax layer at the end. So what I've done is I took the embedding layer out. I don't want to train a new one. I'm going to use the same pre-trained model from the previous notebook, and because I'm not going to change those weights, I'm not going to make that as part of the backprop. I added it as part of my transformation, so I just do it once and don't have to keep repeating this pretty expensive step. So that's why it's inside my preprocessing here, if that was confusing. But I put this all under transform, and I can go ahead and basically just call that, and I apply it to both of my data splits. Okay. Again, in terms of like preparing your data or both data ingestion and this last mile pre-processing, Ray is kind of built exactly for this, and specifically Ray Data and Ray Train. If you're doing other kinds of pre-processing, like let's say from very raw data, not the maybe not multimodal, so I'll quickly cover it. But if you're dealing with a lot of structured data, you're probably going to do joins and filters and aggregations. You should probably do this outside first and then bring it in. But I will say with Ray Data, we are adding support for doing things like performant joins and filters, but traditionally it's meant for kind of this last mile processing. I'm actually going to go ahead and take my data and write it to my storage here, only because I just want to be able to call it from the save location and not redo the workload over and over for every batch in my training workload. Okay, and again, more best practices here. I like to kind of store results, especially intermediate results that I'm going to want to keep track of later. I just like to store them. So again, I'm not redoing the entire workload every time something downstream needs it. Okay, I'm going to kind of gloss over this. This is just basic PyTorch code. Define the model. Um, you can see here the forward batch already expects the embedding output to come out. So that's what's happening here. I defined a couple utilities to save the model, save some of the parameters, stuff like that. So nothing new there. Let me just point out maybe net new things that you'll have to do if you actually want to scale out this model training workload in a distributed fashion. So nothing new here. I'm just applying some collation on top of that. It's all covered in the PyTorch docs. I do use the model registry. I'm just doing a local setup with my MLflow local setup here where I'm just going to drop the checkpoints there. Um, I specify my hyperparameters, again, no tuning. This is the main thing to focus on, how I actually want to scale this. So all the code that you saw is just base PyTorch, but here's the first kind of scaling piece here. Again, I specify how many workers I want to use. You can change this based on what you see in the dashboards maybe. I'm specifying, what kind of, whether to use a GPU, how many resources per worker, and I also do accelerator type as well, but you can leave some of these things blank and you can use kind of whatever is available in your cluster. I have the kind of epoch uh, definitions, like what you should do for each epoch, forward and backward fast. And I think the only last thing I want to point out is maybe I dump all the metrics and model checkpoints to MLflow. So far nothing new except that one scaling config that you saw. Again, we have a lot of guides that show you the high level delta for actually using Ray Train on top of your PyTorch code, but you saw it was just a scaling config. So once you have all this configured, I read the data that we just saved, the preprocessed data. I then set a few parameters and then I call my trainer. I just pass in everything that we just defined and I call trainer.fit. That's it. So all the work, if you were to do this yourself, let's say with DDP or something, of setting up the different worker nodes, if you're doing something more complicated, maybe you'll want to accumulate those gradients and stitch them yourself. All those things happen out of the box, including checkpointing as well. If something did go wrong in your training logic or some worker node dies, the ability to resume from the previous checkpoint or the previous best checkpoint is all extremely easy with ray train here, and that happens out of the box for you. I just ran this a little while ago, so uh, did about like 20 epochs, so not a ton, but enough to kind of get a decent model. And you can see here what we did. This was a multi-node, multi-GPU setup. I use entire resources, but you can also, you saw the workers per node, you can also make that fractional if you are dealing with smaller models or even smaller parts of models. You can kind of separate them out and specify them that way. We're using one type of GPU, but again, you can see here, you can specify different types of GPUs, and then in your scaling config, you can specify what type to use right there. Um, and there's a lot more features, especially if you're doing more complicated things, like you want to define, let's say, different tensor parallelism or data parallelism values for different parts of your model, and you want to jointly optimize them, things like that. We have more complex features with Ray. That one is called compile graphs. So a lot more on our documentation for you to check out, but you saw how quickly we're able to wrap our existing PyTorch code to make this work in a distributed fashion. And just like before, we continue to add more features, especially for the large scale workloads that customers are interested in. So again, with Ray, when you run the same workload, same API on any scale, you get things like elastic training out of the box. So the ability to build scale just dynamic number of workers and continue on fewer resources if something were to happen even on spot instances that you get that out of the box. And then just like the data dashboard, we have a train dashboard as well. And you can see again utilization of all the different things, same as the open source dashboard, but more importantly, you have everything kind of unified and you can see logs per worker across all workers. Um, and be able to make decisions like, hey, I actually need to scale up my concurrency so training happens a bit faster, or whatever else, whatever you're optimizing for. And again, I dumped everything to MLflow, so I just kind of view the different experiment details and GPU utilization, and you can use this kind of information to figure out like, hey, I'm actually underutilizing my GPUs. Let me increase my batch size, for example, and you're able to in real time see the updates here. Okay. Um, Last thing is I think I just get the best run from MLflow, so I know the exact run to use. And just like before, we can wrap all this up as a production grade job. So again, take the code that you ran. I have the scripts here, specify the dependencies and the compute config, and that's it. You can now use this to submit the job. You get again the same thing as before. You can view what's happening, and you can reuse this job. Let's say you want to retrain the model once every day. Just add this as part of your DAG, and it'll just compute retrain the model on new data. I'm going to skip this part. I just did a quick eval at the end just to show the model is at least decent. Okay, let's stop here again before we go on to serving, and then we can do a larger Q&A at the very end. Actually, any other questions here that you guys want to answer?
Um, I think there's a couple of questions around training. So how do you debug with breakpoints with the model forward pass, especially finding problems among layers while training?
Yeah, that's a really good question. I'll share like my personal best practices. So the difficult part about breakpoints is that the distributed so you have your PyTorch code, and then when you use Ray Train, there's a lot of utilities that Ray has, and the ideal place to put the breakpoint is inside, let's say, one of those utilities. But we really don't. It's not a good idea to go inside, the Ray utilities and play with it there. You just really should be focusing on your own workload. So we're actually adding a lot of functionality there. We also have I don't think I highlighted it, but we have a distributed debugger that where you can put breakpoints within your own code or go inside the Ray utilities and use them as well. And you'll be able to, while the workload is running, like stop there and get all the state up to that point. So we're trying to make the debugging experience just like you would on a local laptop. But coming back to my personal best practices, I personally would write the PyTorch code first and just run it on your single head node first. And you're not doing large processing, so it could even be on a CPU, or if you want, you can have one worker to see what that looks like. Make sure that your core PyTorch logic works first, and then you can try to wrap it with the torch trainer from Ray train and then scale it out. But um, that should address the vast majority of your workload specific issues. But if they're Ray train issues, then using the distributed debugger would be the way to go. Any other ones, actually?
Yeah, so there is another question. What are the most common failure patterns any scale has observed when customers run large scale model, multimodal training or inference on Ray? And how do you mitigate these?
They're asking like in general, what are the main issues?
Yeah, what are the main like failure patterns and issues?
Yeah, I personally done a lot of these myself as well, so I'll quickly roll through those. So, um, one big one is trying to combine everything into one workload. So you guys saw how we did pre-processing. Sorry, we did ingestion. We pre-processed the data, and then I stored it, and then I did the model training. So imagine we didn't do that, and I just pulled from the raw data source, did all the pre-processing, and then immediately went on to training the model. Um, one kind of harmless thing, but maybe pricey thing is that if you did combine all those together, every batch, if you don't set things up right, every batch you'd actually be recomputing the embeddings over and over, redoing the reprocessing, and that's a lot of waste there. But the harmful thing that could happen is that maybe your first few batches work okay, but you've now combined all these like CPU-based processes, GPU-based processes all inside the same cluster. And what can happen is maybe after first few batches of your model, we call it back pressure, where there's a lot of processing happen here, and it's basically kind of choking something else upstream that should be happening normally. So it's just overall a good practice to try to separate your workloads. And that way it's better for kind of observability and debugging too, because if you do need to scale out any of those things, it's a lot easier to say, here's like my scoped workload that I'm looking at and inputs and outputs. Um, but yeah, usually when people are combining things, that's there's a lot of room for improvement there. The other thing I would mention is just when you're like defining things, I glossed over our object store. It was a best practice in the batch inference notebook, but a lot of times when you're defining a class or something, just make sure that you're not like creating a new instance of the class for every call or something. You'll quickly see on the observability dashboard that the amount of memory you have in your cluster just is like dwindling very quickly. So again, observability is a really good idea, a really good tool to use to see if you're doing something funky. But yeah, I would say these are the main ones. Are there any other ones, Akshay or Balaji, that come to mind for you guys for like training failures patterns?
No, I mean there's the general like node failures, which is what just having like good recovery mechanisms
Yeah.
that retrain helps you with. And I think another piece is sometimes out of memory issues.
Hmm.
So being able to um, use raise memory scheduling primitives well, they're also making sure like using the observability and making sure your code is not having any memory leaks and so on.
Yeah. Yeah. All right, let's move on to serve, and then we can do a more after the serve one. Maybe we'll open it up to like a general Q&A. Um, okay, so what I'm gonna do here is basically take the model that we trained, we'll load it back up, and then we'll set up a kind of online service that we could then use as an endpoint to get predictions out of. So before I actually talk about Racer, I'll just show you what the code looks like. So I'm using Fast API here. You don't have to, but it's really easy to just wrap an existing Fast API that you've already API service you've already defined and scale it out. So I first define a class called class predictor, but it just loads the model, the pre-trained one, the clip one that we had for the initial part of our model, and then my model itself that we just trained. And I basically just do the forward pass to get out the probabilities for an input. And you can see here I have this decorator called serve.deployment. And here for this specific class here, we can specify how we want to scale it out. So I set the num replicas to 1. I'll talk about how to maybe not hard code this in a bit. Then I also set up kind of what are the actual actor options that I want to specify here, how many GPUs and even the accelerator type. So um, before I get onto like actually deploying the application, this application is very simple in the sense that it just takes that image, the endpoint takes the image and then does a forward pass and gives you the probabilities. But RayServe makes it extremely easy to kind of do whatever logic that you want. So imagine having the same thing as now, but maybe a much more, it's a longer or more complicated pipeline. You can just define this in Python and just chain these things together. You can also maybe have an ensemble of models where you're getting outputs from two different models and they both get combined for a third model to process whatever it is. You can also have business logic. I initially had this example. It was maybe a bit more complicated, so I removed it. But I initially used, if you guys recall, my dog from the embeddings generator. There were some smaller dogs that came up, and it doesn't look anything like my dog. So I actually used the classifier first to generate what classes of dogs my dog could be, and then I used that as a filter uh, before I did the embedding based similarity search. So that actually generated dogs similar to my dog that were actually my dog's breed. So that kind of logic to be able to define it in just Python in a couple lines and then just have it live in your application is extremely easy to do. And then you can also do more complicated things as well. Okay, so to actually define the app, I just use Fast API here. I define the ingress here, which again for us is just that classifier that we defined above, and I go ahead and uh, just call it here to generate the probabilities. I get the model that we stored in our MLflow registry from earlier, and then I go ahead and define the app and I run it. I'm running this locally first. So once it comes up, I send the same image of my dog and I get out the probabilities. So you can see it's much better. She's actually a border collie, but I think the colors, this model probably could be even a bit more better, but much better than getting kind of unrelated breeds, I guess. Um, so that was like the actual serve application. I wanted to show maybe quickly what's happening under the hood now. So we took our model, we just wrapped it with Fast API and just extremely easy to deploy it and also specify how you want to scale each of these things. So imagine we had not just the class predictor, but maybe another model that we're using for something else. I could define exactly how to specify each of these different deployments independently, and then you can now use them all, connect them all into the same service, and you can define again whatever pipeline or ensemble that you want. Um, this is great to just have to avoid having like one big service where it's all all the different deployments you have in there have, you don't have clear resources defined. They're all kind of potentially wastefully using resources. And you saw earlier, I was using I think one whole GPU, but just like before with all the other configs that you set up, you can use fractional resources here as well, which is great if I'm doing something very minimal. I probably shouldn't be using an entire GPU. And that's actually not possible with a lot of other solutions right now. I also have, you saw before we had the num replicas. When you're running this on any scale, you can actually set num replicas equals auto. And that would actually just scale your service up and down based on the traffic that's coming. And we use Fast API here, but you can define your service a bunch of different ways and easily wrap that stuff up. There's more complex features that Akshay and his team have developed over time. There's like dynamic batching, where if you want to wait until a critical mass is built up, then actually do the call. It's up to you. And then we also have actually not just for serve, but for data train and serve, very similar utilities when you're working with large language models. I think we will, or we've already had a webinar on that, but we have great documentation around that as well. Okay, last thing I'll mention again around if you're doing the same Ray workload on any scale, you get a couple more things out of the box. So even faster auto scaling and model loading as well. We have a couple benchmarks here, but this is great if you want to, especially if you're kicking off kind of, if you're scaling up, these are going to add up. We've got some metrics around QPS and tokens per second for, again, for LLM use cases as well. Um, there's a couple, maybe another thing to note is call it replica compaction. So the ability to just like take the workload that's happening and just run it on fewer nodes when it's possible. And this way, you don't have a bunch of different things just running in a fragmented manner and kind of wasting a ton of resources. You can actually pull that all back together and just run it on, um, a few highly utilized resources. We've got a bunch more on kind of, again, I'll show you guys when we talk about the production grade services, but the ability to upgrade your service without any downtime. So let's say I have served the same service here, V2 with a better model. I don't have to shut down serve the V1 and wait for V2 to spin up and have this like moment in the middle where there's no service available. You can roll these things out. You can actually monitor what's happening as well and decide not to roll it out, whatever you want. And again, a lot more around governance and admins here in terms of using different environments and availability zones. Um, you guys can check that stuff out in the docs. So again, a huge observability dashboard here in terms of utilization, queries per second, latencies across different granularities, whatever you want. All this comes out of the box for you. And you can connect this again with your if you are using your own real-time monitoring systems as well, you can port all these metrics over. And then again, the same thing when you are doing this on any scale or if you're doing it anywhere else, you want to be able to run this in production. And any scale has services here again for rollouts and updates. And we have a designated view for all this as well. And this, I was actually just rolling out an updated service, and you can see it's slowly using Canary deployment here to roll out the next version. Okay. Again, to actually do that, it's very similar to the jobs API here. Just wrap, again, take your code, specify the compute and dependencies, and be able to launch it as a service. Last thing I'll mention is kind of you saw all these jobs for the batch inference, and then the training, and then now we have a production service. You can see you can treat all of them as just nodes in your DAG, whatever the node workloads are, and now you can use them in your workflow. So if you are using another orchestrator to hook all these workflows up together, jobs and services just become very neat nodes to define and just have them execute as part of your larger workflow. Okay, that's all I have for serve here. I guess maybe we can do actually serve first questions, or we can also open it up to kind of generic questions. And again, all this will be shared with you guys afterwards.
Yeah. Cool. So I can also take some of these. So um, the first question is for inference, is it possible to do something like AWS Lambda where you run when required and stop? And how to keep GPUs up at all times versus for small scale. So yes, so Racer does allow you to scale to zero. So it can queue up requests internally it has scaled to zero while it scales up the new GPUs or replicas to serve the traffic. So it's definitely possible to do something like run when required and stop when there's no traffic. Okay, next, there is a question around for inference-heavy multimodal pipelines. Why should customers choose Ray over other inference orchestrators like BentoML model or CoreWeave's serverless APIs? Um, so Ray's experience is very Pythonic, and so the way like BentoML and so on work is they visualize the deployment similar to microservices. So you're like deploying multiple different microservices, which are like your different models. But with Razor, you're kind of deploying everything as one application, so that make sure you only have like one set of deployment to manage, observability to manage. There's easy backwards compatibility as you're upgrading your application. But you can still scale each of the individual components independently with Reserve. And it has built-in auto scaling, scale to zero. All the routing and stuff happens within the framework. So it allows you more flexibility in how you can compose your pipelines. You can do branching workflows, different types of um, workflows as you're orchestrating multiple components, but you can still manage it as one single service. Anything to add, Goku?
No, I think that's perfect. I something else that I really enjoyed is I didn't cover is defining how you want to scale all these things. You can do it in the code, separate config, and just the plethora of ways to define all these things. But yeah, to me, it always felt like the advantages of microservices without kind of the fragmentation of microservice setup.
There's one more serving question that's around Ray handling KV cache, prefix caching, or can we use VLLM or SGLang with RayServe? Yes, so we do have some RayServe LLM specific APIs and deployments built out for you. So you can use it with like the OpenAI compatible APIs and deploy VLLM with RayServe. And then part of the roadmap is we are also adding prefix cache aware routing that will be available soon. And then more advanced large scale serving patterns as well, like prefill disaggregation or DeepSeek style MOE serving and so on.
Yeah, I didn't cover it today, but we have a lot of utilities specifically around LLMs as well. But I think you'll see it on the individual libraries documentation. You guys can check those out.
I think that's it in terms of serving. There's a couple of general questions. Um, so let's take this one. Are there any performance bottlenecks or failure modes when scaling beyond 1,000 plus GPUs or 10,000 plus cores in multimodal pipelines?
Biology, I think you personally work with some customers that have done 10K plus nodes. Any kind of lessons or failure modes you want to highlight?
Yeah, this is for array data in particular.
Yeah.
I think yeah, so up to 10,000 nodes. I think generally we should support that scale okay, at least with Ray Turbo. I don't think we've seen any, yeah, really like unique problems at this scale. I think for the most part, Ray data scales pretty linearly with a number of nodes.
Mm, yes.
But yeah, one thing to call out, I do think open source Ray though it has some scalability issues, so you might start hitting some yeah performance issues at like the 10,000 node scale.
Mm. Yeah, whoever that was, if you guys are doing more than that 10,000 scale, you should definitely reach out to us.
Cool. There's one more question around for multimodal data sets that are at the order of petabytes. How does Ray handle data locality, caching, IO bottlenecks in cloud environments? Um, so this is a little bit outside Ray itself. It's more like how where you run your clusters and jobs and so on. But yeah, you can integrate with um, EFA for data loading and other like these cloud provider set of utilities to have faster data transfer. And you can definitely set up your Ray clusters with those. Cool. I think we're out of time for questions. So any final words? Go.
Yeah, again, we'll share all this to you guys, but if you have more questions just about Ray in general or Ray with any scale, you guys definitely join we have a Slack community for Ray as well. Definitely join there and ask all your questions. And if you guys are interested in some of the more Anyscale specific features, reach out to us, any of us here, or through the anyscale.com website, you'll be taken as well. I do want to call out this whole like Anyscale platform is free for you guys to try out. This entire notebook you can run through multiple times and still have plenty of credit left over. So highly encourage folks to run this on Anyscale just because you don't have to worry about the setup, all the dependencies and compute. And if you guys like it, that'll eventually lead to a conversation with Akshay and a few others on kind of how your specific workloads could be improved and your entire ML platform setup could be improved a lot more. Awesome. Thank you, everyone. We'll see you guys. And I think we're going to have more webinars pretty regularly. So the next one coming up is around actually leveraging RayServe to scale out MCP tools and servers themselves. So that's interesting. You guys should join that one in a couple weeks. Awesome.